Hey everyone, in this lesson we are going to discuss the half-cut cell in the PV system. So before we start this video, if you are new to our channel, don't forget to subscribe to our channel in order to get all of our last videos. So let's start by discussing first what is the meaning of the shading effect before we go to the half-cut cell. So what does the shading effect mean? The shading effect means that there's a shade or a shading effect on the PV panels. So what I mean by this, if you have a tree, for example, you have a chimney or any roof component, all of this provides a shadow. You will see here a shadow over the PV panel, or the fallen leaves from the tree going on the panel, okay, or the tree itself providing a shadow over the panel itself. All of this is called the shading effect on the PV system. So what is the effect of the shading on the PV system? You know that the presence of shadow on the PV system reduces the output power of the PV panel. Usually you will find that the PV panel shading here, for example, for this part, can reduce the power of this panel by 33%. Okay, we will understand why 33% in the next slides. So the shading effect, as you see here in this example, we have unshaded cell like this one, okay, PV cell. Now this PV cell will provide the 100% current and voltage according, of course, to the temperature and the irradiation falling on it. Okay, so it is working by 100%. Now if we have a partially shaded cell, a part of the cell is shaded by the effect of tree, leaves, whatever, here you will find that the output current of the shaded cell is directly proportional to the illuminated area of the cell. So according to this area, the power or the current generated depends on this illuminated area, okay, and no voltage change. The voltage will not change depending on the shading effect. Okay, so the voltage is constant. The variable here is our current. Now in the completely shaded cell there will be no current, so it will be zero, so there will be no output. Okay, now let's see an example. We know that, or we discussed in our course for solar energy, that in order to prevent the shading effect on the PV system, we can use something which is called the bypass diode or the bypassing diodes, like here. What does this bypassing diode do? You will see that here, for example, this system, we have 1 panel, 2 panels, 3 panels, 4 panels, okay? So this system consisting of a group of panels, usually here in this example 10 panels, okay, in this example. Now you'll see that this panel is working okay, so the current will flow through this panel, okay, and this panel also working okay, so the current will flow through it. Now but this panel, this one, is shaded, okay, or partially shaded, okay, so the current produced by this panel is very low. Okay, so in order to cancel the effect of this panel, we will use the bypass diode. Okay, the bypass diode will allow the current to flow and bypass the panel, okay, as if this panel does not exist, provides a passage for the current. Okay, and then you will see that this panel is working okay, so the current will flow through it. Okay, now you will find here in this example we have by using the bypass diode and the lower one without using the bypass diode. So if we don't use the bypass diode, what will happen? The problem here is that all of this panel, here we have 10 panels and here we have 10 panels. The above panel or the above 10 panels are connected in series. Okay, all of them are connected in series. So the current flowing through them is similar to each other because they are in series, so the current is same through them. Okay, so same current means that we will have the same current flowing through them, but here the current will depend on the panel. So the shaded panel, if we allow the shaded panel in this case, this shaded panel will produce lowest current. In this example, it will produce 1 ampere. Okay, so what will happen is that all of our system or all of our connected strings will produce the lowest amount of current, which is 1 ampere. Okay, they are forced to produce 1 ampere. The current flowing through them is similar to the lowest one, which is 1 ampere. Okay, but in this case, when we bypass the panel, we provide the normal current, which is 8 ampere. Okay, so the 8 ampere is the current of this one, this one, this one. Okay, but this one is cancelled, so it does not have any effect on the current. So now we have 8 ampere, which is the current flowing through our panels, multiplied by 32.5 volt, which is the voltage of one panel, okay, produced by each panel because they are in series, and 9 is the number of panels. Okay, we said that we have 10 panels, and since we bypassed or cancelled the one panel, so we have 9 panels. So in this case, we have 9 panels in series multiplied by 32.5 to give us the total voltage, multiplied by the current flowing gives us 2340 watts. This is the output power of this system. Okay, now let's look at the lower one without the bypass diodes. Without the bypass diode, we have 10 panels. Okay, we didn't cancel this one, so we have 10 panels multiplied by the voltage of each panel. We know that the voltage is not affected by the shading effect, so we have 32.5 volt, but the factor here is the ampere. Ampere is forced to become 1 due to the presence of shaded PV panel. So this will produce a power of 325. So the power here is reduced compared to the first case of the bypass diode. So this is why bypass diode is important and existing in our PV system. Okay, so sometimes the bypass diode here, usually here, for example, this panel, each panel has, for example, 3 bypass diodes. Okay, in this example, we say 1 bypass diode, but actually it can has 3 diodes. Okay, or 3 bypass diodes. So by using the bypass diode, we cancel the shaded panel, and we now have in the first case 9 panels instead of 10 panels, but with a higher operating current of 8 ampere. But in case of the shaded panel, the second case, the number of panels would be higher. It can be 10 panels. However, the current will be reduced to 1 ampere due to the shading effect, and we select the current based on the lowest panel produced current, or the lowest panel producing a current. Okay, so the total power will be reduced in the second case compared to the case of the bypass diode. Now, there is a new technique which have been developed since 2017, as I remember. This technique is called the half-cut cell. So what does the half-cut cell means? We have here, for example, the full cell monocrystalline, a normal monocrystalline panel. You will see that it consisting of full cell. Each of this block is considered as a cell, one complete cell. But the half-cut cell, what does it mean? It means that we are converting the standard cell into 2 halves. By cutting it using laser, we cut it into 2 equal halves. Here a half, here a half. Okay, now producing something which is called the half cell. So our system here is consisting of 2 panels integrated inside one panel. Okay, so you can see here this is considered as a half panel, and the lower part half panel. Okay, the upper one consisting of half of a cell, half cell. This half is similar to this half. That's why it's called half cell monocrystalline, and the lower one consisting of half cells. Okay, so basically we divided or cut each of this cell to half, and provided two panels integrated in one panel. Okay, so this panel produces the same power as this panel. Nothing changed except that we separated the panels, okay, or separated the panel into two halves. Okay, now something important here is that the panel full cell monocrystalline, in this one we had one junction box similar to any normal full cell monocrystalline or polycrystalline or any type. You will find here one junction box and two terminals, the positive and the negative. The junction box contains the bypass diodes. In this case here, for example, we have 3 bypass diodes in this panel. Okay, so one bypass diode for one string, this two column, this column and this second column forms one string, and we add to it one bypass diode. This column and this column, we make it one string and provides for it one bypass diode, as we will see in the next slide. Don't worry, we will understand the string and the number of bypass diodes. And here this one and this one, these two columns forming one string and one bypass diode. All of these diodes are contained in one complete junction box, this one. But in the half cell monocrystalline, we have, similar to the full cell monocrystalline, we have 3 bypass diodes. Okay, but each of the bypass diodes is contained inside a junction box, a smaller junction box. So this is a junction box, inside it one bypass diode. This is another junction box, inside it a bypass diode, and this is another junction box. Okay, so you can understand the difference here. The first thing, we divided our cell into 2 equal halves. Okay, then we divided our panel into 2 equal halves with half cells. Okay, and we now see that the diodes are similar to in both cases, but in this case we have 3 bypass diodes contained in one junction box, but in this case we have 3 separate junction box, and each one has one bypass diode. Okay, so I would like to see the difference again, or what makes the difference here. Here we have 60 complete cell. This is a full cell or full cell monocrystalline. Okay, one complete cell. Okay, so we have here 60 cells. You will see that here we have 3 bypass diodes. All of this are contained in one junction box. Okay, now you will see that each diode takes one column or 2 lines here. Okay, so our panel is divided into 3 strings. This is a string, this yellow one is a string, this yellow line. The current flows here inside the cell and goes back, then flows through the gray one, like here, goes up, then flows like here, goes down, and then up. This is our second terminal, this is our first terminal. Okay, now we'll see that here each 2 lines representing or protected by a bypass diode, okay, or separate by a bypass diode. Okay, so in this case we have 3 strings. The 3 strings contains 3 bypass diodes. Now what will happen if we have a shading on this the first 2 panels, 2 columns of cells? What will happen is that this bypass diode will not allow the current to flow here. The current will flow through this bypass diode and cancel this part. Okay, let's draw it. So the current, instead of going here, it will go through the bypass diode like here, assuming that these 2 cells have a shading effect, so we can cancel them. Okay, and the current will flow here and get back normally as we discussed at the beginning. But since we cut 1/3 of the strings, we cut third of the strings, what will happen in this case is that our power will be reduced by 33%, right? Why 33%? Because we cut 1/3 of the panel. Okay, so here the power reduced by third. Okay, now in the second case here, we divide the 60 cells into 2 equal halves. So since we divide it into 2 equal halves, then we will have 120 half. Since we have a 60 multiplied by 2 gives us 120 half cut cells. Now in this case you will find that the bypass diodes are in the middle of the panel. Okay, in the white line, as we saw before in the previous slide here, this line, this white line contains the bypass diodes, as you see here. Okay, now you will find that these two cells, this first panel and second panel, or the two half panels, are parallel to each other. Okay, they are parallel. Each of them takes half of the current. Okay, since this is our first terminal and this is our second terminal, so the current goes here and goes up and goes down. So the current is divided as if we have two panels. Instead of one panel, we have two panels. Okay, but now let's see what is the difference here. The difference is that we have now 6 strings. Okay, 3 on the top and 3 on the bottom. Okay, you will see here 1 string, 2, here 2 and 3, and similar here at the bottom, 1, 2 and 3, like this. Okay, so we divided our panel into 6 strings or 6 parts. So now if we have this part have a problem, then the current will not flow through it, but it will flow through the bypass diode. Now this part only is considered as 1/6 of the panel. So now the power is reduced by just 1/6 of the power. Okay, since we divided the panel into more number of strings. But in this case, when we had only 1 string, then the power is reduced by 33%. So now the efficiency is improved. Okay, if we have a shading effect, then just part of the panel or 1/6 of the power will be reduced, compared to the full cell where at least the third of the power will be reduced. So in the first case of the 60 cells, as we see here, you will find that the power is reduced by third, which means we are losing the third of the power. Why? Because it is divided into 3 strings by the bypass diodes. In the second case of the 120 half cut cells, we lost only 1/6 of the power for each part, since we divided the panel into 6 strings. Okay, so what are the advantages of the half cut cell modules? Number 1, the power loss is generally proportional to the square of the current times the resistance. Therefore, when cutting a solar cell in half, the power are reduced by a factor of 4. So where did we get this? Okay, so remember that the electrical losses or the power losses inside a PV panel or any electrical system, it will be equal to the current square multiplied by the resistance. Okay, so this is our full size. Okay, and this is our half cut divided into 2 panels. Okay, the panel itself is divided into 2 halves. Okay, now remember that here in the first one, the total current passing through it. But in the half cut size, half of the current flowing here and the other half flowing through here. Okay, so what does this mean? That the current here is half. Okay, so the current is reduced by half. So half square, or the square of the current, which is now reduced by half, will give us quarter. Okay, which means that our losses will become 0.25 or 25% of the old losses. Okay, so the losses now is 25% of the old one. So this means that the power is reduced by 75%, the losses reduced by 75% compared to the full size case. Okay, so that is the first advantage in using the half cut cell modules. When the area of the solar cell is cut in half, the amount of electrical current of each bus bar is reduced by half as well, as we discussed. This decrease in electrical resistance within the bus bar results in an over increase in efficiency. So someone will ask me, how did the resistance is reduced, or how did the resistance reduce? Okay, remember that we have here one complete cell, okay, one current, complete current flowing through it. Okay, now these two halves, what is the connection between them? We said before that the connection between them is parallel. Okay, these two halves are parallel to each other. Okay, so what does this mean? It means that if this one have a resistance R and this one have a resistance R, and they are parallel to each other, then the equivalent resistance will be R over 2, since they are parallel to each other. Okay, so that means that the total resistance in our system will be reduced. So this will also increase the efficiency of our PV panel. So the actual increase in the efficiency per manufacturer varies in the range between 1.5 to 3% efficiency increase. So as an example, if we have a monocrystalline with 18% efficiency, then the new efficiency will be 19.5 up to 21%. Okay, so this is a large increase in efficiency, and there is no difference here. You have the same panel with the same power, just cutting it into half will provide you more efficiency in your own system. Now another important advantage here is that we have improved heat dissipation, not high dissipation, heat dissipation, as we are using 3 separate junction box instead of just one box. You will see here 1, 2, 3. So each of them has one bypass diode. So it means that the heat dissipation in each of them is reduced compared to having one junction box contains 3 diodes or 3 bypass diodes, and the current flowing through them means that we will have high heat dissipation. Now with half cell modules, as we discussed here, each cell is divided into halves. You will see that according to the analytics, is that in 2017 we just had 4% of the for half cell. Okay, we had full cell as you see here, and the half cell with the orange, and quarter with the near yellow. Okay, the quarter cell, there is also a quarter cell. Now you'll see that at the beginning in 2017 we had only 4%. As time passes, the percentage of the half cell will increase. We predict that at 2018 that the market share for the half cell will jump from 5% in 2018 to nearly 40% in 2028. Okay, so this is a huge change inside the market of the half cell modules. So in this lesson we discussed the half cell modules, the shading effect, and the difference between having bypass diodes and without bypass diode, and why half cell modules are the future, or why are they important. So before we end this video, if you are new to our channel, don't forget to subscribe to reach all of our new videos, and if you like this video, don't forget to give us a thumbs up. Thank you and see you in another lesson.